Perfect. So welcome everybody to the Highlights Beyond SIGMETRICS session. This is a session that I guess it's the second time we've run it. It's a new initiative still at SIGMETRICS, which is trying to highlight work in related conferences that appeared in a related conferences, but that kind of has that SIGMETRICS flavor and that we feel will be interesting for the SIGMETRICS audience to be aware of. And so it highlights both connections between people and conferences and areas with the SIGMETRICS community. And so we have 3 talks that we selected here. These were selected by a committee appointed by the SIGMETRICS board, which included me and Rashid Agrawal and Sid Banerjee. And the goal was to connect to impactful papers from top conferences in other areas within the last year. And so we selected 3 such papers, one coming from the systems community, which is going to be our first talk, one coming from the applied probability community, and then one coming from the learning community. And so we'll start with our first one, which is going to be presented by Chunlam Lao. So Chunlam is a student at Tsinghua University under Wenfei Wu. And this is a paper with, and it's a big collaboration between the Tsinghua group as well as Aditya Akela's group at Wisconsin. And so there's a number of co-authors that you can see on the slide. And this was the best paper recipient at NSDI this year. So Chunlam, take it away.
Thanks, Adam. So thanks for the chair. And so let's get started. So I am Chunlam Lao from Tsinghua University. And today I'm glad to have this opportunity to present our work at SIGMETRICS 2021. Okay, so before started, I want to have a brief introduction about this work. So what we did is actually a networking service that target to accelerate the distributed training process, and we target to a multi-rack setting, multi-talent setting. Okay, so so let's get started. So first of all, I would like to introduce some of the backgrounds of distributed training. So this is the typical PS architecture for distributed training. So there are 2 main roles. So the first one is parameter server, and the other one is the workers. So in each iteration, the workers will compute its part of gradients and then send its part of gradients to the PS. And then the PS, when the PS receives the gradients, and then it will do the aggregations, and then send back the unified update result to all the workers, iteration by iteration, until the model is convergent or until the end of the training. Okay, but in this scenario, is it echo? Okay, so in this scenario, the network can be a bottleneck for this architecture. So because you can see this obviously you can see in-cast problems when multiple workers trying to send traffic to the parameter server. Okay, so what we did actually is we want to place a programmable switch in the middle of the between the parameter servers and the workers, and then we do the aggregations inside the network. This is what we want to do to leverage the bottlenecks of distributed training. Okay, so before I start to talk ATP, I would like to talk about some trends of in-network computation. So this is a typical architecture for a programmable switch, and the packet will come in from the packet ingress, and then flow many match action unit, and then send out flow the packet egress. So nowadays, with the advance of the hardware, so we can have some register inside the programmable switch. So at this moment, and we can use this register to perform aggregation and store something into the registers. Okay, so what we did is actually we move the function of gradient aggregations into the network, into the programmable switch. And so finally, so our process becomes when the workers trying to send packets to the parameter server, the gradient packet, and then it will be aggregate inside the switch and then send the result to the PS. And then the PS will send back the result to the switch and multicast back to all the workers, iteration by iteration. Okay, so here, some people might have a question about, so we do the aggregation inside the switch. So why do we still need the parameter server, the end host parameter server? And we can just do the aggregation in the switch and then just multicast back. Yeah, indeed. Actually, there are some fantastic work has been done using this design in NSDI 21 as well. And oh, I forgot to mention about this. So by doing this, by introducing the programmable switch, we can reduce the traffic. Because the traffic has been aggregated inside the switch, and also we can speed up the training because we use hardware to do the aggregations, and also we can release the CPU resources here. Okay, so these are two main benefits for of ATP. And as I mentioned just now, Switch ML they did a PS offload in the switch. They offload the entire PS into the switch, so they don't use end host PS. And then when the worker is trying to send package to the switch, and then the switch will do the aggregation and multicast back. Okay, I will have a brief introduction about Switch ML because our work, ATP, is actually quite similar to their work. And we do some improvement, and we have other designs compared with Switch ML. And the second one, it's Switch ML target at single rack settings. So here's an example. So in Switch ML, they can only do single rack, like all the machines are under switch 1 in this figure. So it is one of the example. And also, if multiple jobs trying to use the switch at the same time, so like this is an example. So if multiple jobs trying to use this switch, and then in Switch ML schemes, they need to do a static partition. So in this example, job 1 and job 2 trying to use the switch to do the aggregation, and then register 1, 2, and 3 will be assigned to job 1, and 5, 6, 7 will be assigned to job 2. So this is what I call static allocation. Okay, so this is mainly what Switch ML does, but we think this approach has some shortcomings. So the first one is they cannot use the switch resources efficiently. So this figure, the figure below, it's a traffic pattern when we launch a VGG16 job. So as you can see, there is an on-off pattern. And I think you might know that the process of the distributed training is actually an iteration of computation and then communication, computation, communication. So when end host is doing the computation job, and then they're not sending any traffic. So if we do the static partition in the switch, and then the switch resources cannot be used efficiently. And also, they does not consider multi-rack settings. So here is another example. Here is the number of nodes that the BERT large models trained need to have. So for the BERT large model, they use 92 nodes, and this number will be increased in the future because the complexity of the model architecture is increasing. So it is crucial to support multi-rec setting. Okay, so the goals of ATP is to speed up multiple jobs, distributed training jobs in a cluster. This is our first goal. We want when multiple jobs trying to use the switch and at the same time, and we can do this, and then we can speed up them, and we can let them to get the benefit from in-network aggregation. So this is the second goal. We want to maximize the benefits from in-network aggregation. So and this is the outlines of the talk today. So first of all, I would like to talk about how ATP supports multi-talent, and second, how ATP supports multi-rec settings. And then I would like to talk about some additional challenges, like how we handle the reliability and the congestion control problem, why we need to do this, and how do we address this problem, and also we need to. I would like to talk about something about the floating point computation, because in current designs, the programmable switch doesn't support floating point computation. So we have to do something before sending it to the programmable switch and to the aggregation. Yeah, and I will talk about it later. And finally, I will provide some implementation details and some evaluation results. Okay, so first I would like to talk about the multi-talent. And I think you still remember the static allocation. So here we come up with an ideas about dynamic allocation. So our goal here is to maximize the switch resource utilization. So this is the figure is the abstraction of switch, and we abstract each right square as an aggregator, and the aggregator is responsible to perform the aggregations of packets. Okay, so if we are using the static allocation scheme and multiple jobs, maybe let's say 3 jobs trying to use this switch resources, and then the switch resources will be partitioned into 3 parts, and each job will get the third one. But in dynamic allocations, we want all the jobs share all the aggregator. We introduce and have hash function to do this. And here I would like to talk about an example. Okay, so so all the workers from a job, the job here means VGG job or a ResNet job. Okay, so all the workers from the same job will share a hash function. So the workers will first compute the aggregator index, and then they will send their packets to the aggregator, to the target aggregator. And then because all the workers are sharing the same hash function, so they will all hash to the same direction. And the workers will send a lot of packets to a different aggregator by hashing into and they will have a lot of aggregator indexed. Okay, and finally, when the aggregator, when the last packet is received by the switch in an aggregator, and then the result will be sent to the PS. And then the PS, when the PS receive the result, it will send out, it will ACK back with the update gradient value to the switch and multicast back to all the workers. So this is a small example for how we do the aggregation inside the switch. Okay, but what I just mentioned is a single job. But when it comes to multiple jobs, let's say we have 3 jobs here and maybe more, and then they're trying to use the same switch. At this moment, job 2 trying to use this aggregator because he have the hash function and then he hashed the aggregator indexed, but he find this aggregator is already occupied by other jobs. At this moment, the job 2, the workers from job 2 will send the packet to the PS directly without doing aggregation inside the switch. And this is what we call best effort. And okay, so our goals here is to let the switch becomes the best effort things. So like when the switch resources is unavailable or it is not enough, then the switch can be a transparent things like the switches no longer exist and the aggregation process can still be done at the end host. And that's why we keep the designs of living PS at the end host. Okay, so so all the workers will be directly forward to the PS, and the PS will do the aggregations, and then the PS will send back the result, like the switch is not doing anything. Okay, so this is the best effort. Okay, and next I would like to talk about how we support interact aggregation, which is so in nowadays the data center have a lot of different policy, different complicated policy like non-deterministic routing like ECMP. So it is not easy to predict the routes, and because we want to do the aggregation, so routing is quite important for ATP. So in order to perform aggregations and having a trade-off between complexities and performance, and then finally we decided to only support two-level aggregation at top switch. And you can imagine the aggregations will be performed at the first layer, first switch, and the last switch. Okay, so here is an example. We have 6 workers, and they are trying to send packets to the PS. And first, the switch 1 will aggregate the result from W1 and W2, and 3 and 4 will aggregate at switch 2, and 5 and 6 will aggregate at switch 3. And then the result from switch 1 and switch 2 will be sent to the switch 3, and the switch 3 will do the aggregation, the last aggregation, and then send back send the result to the PS. Okay, so in our current designs, we can scale up to 1,024 workers. And third, I would like to talk about some additional challenges here. The first one is the rethink of reliability, because the network is unstable, and we need to come up with an ideas about how to handle the packet loss situation. So because we have designed our system with programmable switch, so all these challenges we need to we need to having a co-design with programmable switch. So I think it is interesting, but since we don't have enough time here, so I would like to mention a bit. Yeah, and next I would like to talk about the aggregation, the correctness of the aggregation, because yes, I mentioned the network can be unstable, and maybe there are some resent packet and out of order packets. And how do we handle the switch aggregation is only performed once, and this is important. And we also have some effort in guaranteeing the correctness. And third, memory leak situation. So it is quite common that a job can be handed or just shut down suddenly, the machine is shut down suddenly. So some of the aggregator will be reserved forever, and this is not good. So we add a time step here at the program switch. So when we detect a memory leak, and we can evict the result, and yeah, this is all the designs of ATP. And also we rethink the congestion control problem, because we want ATP can collocate with other background traffic and maybe other application, other ATP traffic as well. So we need to think about the congestion control problem. And also it has a little bit different from the traditional congestion control problem, because the switch do the aggregation. So the flow will be so we have n-to-1 flow. So we need to come up with which congestion signal is better for us. Is it ECN or RTT? Okay, so we mentioned it in the paper. And finally, we did the floating point computation things, as I mentioned. So the programmable switch doesn't support floating point. So what we did is we converge the floating point to integer at the end host, and then send to the programmable switch, and the programmable switch do the aggregation, and then send back to the end host, and the end host will converge this integer to floating point, convert back. So in order to achieve this, we do some engineering work, and we also need to ensure the conversions, the cost of the conversion will not impact maybe the accuracy or the speed of the training job. And we also have some evaluations on it, and also because the representation range of floating point is different from the integer. So it can be, so the overflow problem will happen. Okay, so and finally, I would like to talk about some implementation and the evaluation details. So ATP, actually, I would say ATP is a networking module, a networking library, and we substitute the networking stack of BytePS. So BytePS is really great because they integrate MXNet, TensorFlows, and PyTorch, and they have a PS architecture, so it is easily to substitute with. So we substitute their communication module, and then so we can use TensorFlow, PyTorch, and MXNet scripts to evaluate the real models. And we use P4 to implement the in-network aggregation service, and we use the Intel Tofino switch as our hardware. And then I would like to talk about something about the evaluation. So we have 9 so in the evaluation, we have 9 servers, and each one have a 2080 time GPU, and all connected to the Tofino switch with 100 Gbps NIC. And we compare ATP with BytePS, SwitchML, hardware, and those state-of-the-art system. And we use training throughput and time to accuracy as our metrics. And for all our evaluation, we use the real work model, the image classification model like VGG and ResNet. Okay, so so here I would like to show some of the results here. So this is one of the results. This is the single job performance of ATPs compared with other schemes, other systems. So you can see ATP perform better than others state-of-the-art systems in all the models we evaluate. So we have a small observation here. When the model it's a communication intensive model, and then we can get larger performance gains on it, because they need a lot computation, they need a lot communication, so we can speed up more compared with the computation intensive model like ResNet. And also, we have done some evaluations about our schemes, our dynamic allocation schemes, and compare with the static schemes I mentioned. So we launched 3 with GG16 job, and in the static allocation scheme, they will split they will split all the aggregator into eventually, and you can imagine it. In this experiment, we have a pool of aggregator, and when the pool is getting smaller and smaller, so dynamic schemes can perform better than static schemes, because dynamic scheme allowed all the jobs share all the aggregator, but static scheme doesn't. Static schemes can only partition some jobs, Okay, so here, and also we have some observation, and when the switch memory is insufficient, our schemes, the dynamic schemes, can perform better. And due to the time limitation, so we only show 2 of the experiment here. So if you're really interested in our paper, and then you can find out more results like packet loss recovery overhead, and the time to accuracy things, and the congestion control problem. And we did a lot evaluation here, but yeah, if you're interested, you can refer to our paper. Okay, so to summary, ATP is a network service that supports best effort dynamic in-network aggregation, and it is aimed at a multi-rack, multi-talent settings. We co-designed the end host with the switch logic to design some to address some problems like reliability, congestion control, and dealing with the floating point problem. And finally, we open source our source code in GitHub. So please feel free to explore our code base. And if you have any questions, you can directly contact us, and we're happy to answer your questions. Okay, so I think it is the end of my talk. So yeah, thank you, and yeah, thank you all of you.
Thank you, Chen. I'm going to clap for everybody here. So thank you. At this point, I'm very happy to open the floor for some questions from everybody, and I see a few hands already, so I will unmute, I guess, starting with Z. Let me see, make sure I can do this. I think you can, there you go. I think you should be able to talk now. Mute.
Okay. Hello. The nice talk. So I have a question about the aggregation strategy. So if I understood correctly, which is not a guarantee, you end up aggregating the sort of gradients perfectly. So like you guarantee that you're going to faithfully add up all the gradients and not have any errors in how that's added up. Is that correct?
It is an ideal situation, but when it comes to some problems, and we can have other schemes to recovery from that.
Okay, so I guess so. What my main question was have you? So I know there are some machine learning systems for distributed settings that basically don't guarantee that they're going to perfectly aggregate the gradients. Things like Hogwild is the kind of classic example of this. And I was wondering if you have investigated whether those sorts of trade-offs might end up giving a net performance win for your system.
Yeah, that is a really good question, because yeah, also I have seen some papers mention about some loss of the gradients will not impact the result a lot. And then, but in ATP, yeah, we can do it, but we want our goal is to want to preserve the primitive of the primitive of reliability. So we don't want the upper layer to concerned about the lower layer. We want to deliver their intentions. So finally, we only do a reliables, and we will keep all the aggregations. And if there is something lost, and then we will and then we come up with ideas to aggregate them instead of just leaving them yeah.
Great, thank you. And then we have another question here from Isaac. So Isaac, you should be able to talk now to ask your question.
Hi, yeah. Thank you for the talk. It's really interesting.
You're quiet, Isaac. If you can get closer to the mic, that would be helpful.
Does this sound a bit better?
A little bit, but it's still pretty quiet. Can you hear him, Chonglin?
A little bit.
Okay, I'll repeat the question then.
This might help.
That's
Okay.
better, yes.
What I was wondering is, beyond just like addition aggregation, are there other aggregation primitives that one could implement? Like, in other words, can this only implement aggregation primitives that are like very simple, like addition, or could some more complicated function be used as long as it was, you know, maybe associative or commutative or had some other properties like that?
Yeah, well, actually, it is really great because so programmable devices like the programmable switch, they need to forward the packet at light rate. So the hardware is designed to be easy, and I can say the programmable switch doesn't support some easy operation like multiplications. So yeah, they cannot perform multiplication, and also they cannot perform floating point. And but for aggregation, just some additions and maybe some XNOR and XOR, and this kind of bitwise operation is allowed. And yeah, I think it is quite limited, but I think in the near future it would be better. And for more application, and yeah, nowadays the programmable switch is the limitation, I think.
Okay, thank you.
Perfect, thanks. I think I will end the question and answer period there so that we stay close to time, and thank Chonglin one more time. Thank you. So Michael, I'll invite you to unmute and turn on your video and come onto the stage and share your screen while I introduce you. So our second paper is from a different area that SIGMETRICS overlaps with. So that's the goal of this session, is to expose us to related fields. And so, you know, NSDI and SIGCOMM, you know, we all are familiar with on the system side, but on the sort of theory side, the SIGMETRICS community is very connected with the informs operations research community, and you know, often the applied probability part of that. And so that's kind of the you know, the area where this paper was born, and the paper has received some best paper awards of various shapes and forms from that community over the last year. And it's, as you can see, it's a very timely topic. And this is a paper with an extremely long list of co-authors. I was hoping you would put them on the slide, so I would not have to read them all, but I will just point you to the program to see the long list. I believe, you know, let's see, do you have, I think that they are, you know, 10 or 20 co-authors of various forms, including true epidemiologists and theorists and control theorists. And so this was quite a nice collaboration in terms of the project. And I'll let you, Michael, take it from here.
Thank you, Adam. Actually, you know, I was a bit lazy myself, and I put it as part of COVID analytics because, as you said, the co-author list of this entire project, sort of project under COVID analytics is very, very long. So, you know, please feel free to, you know, go on to the covidanalytics.io to, you know, to see the full list of collaborators that we have, you know, throughout the many facets of the project that we have worked on. So, you know, thank you again, Adam, for inviting me. And so today I'll be talking about forecasting COVID-19 with application to vaccine trial design and distribution. Now, unfortunately, I think no one needs any more introduction to what the COVID-19 pandemic is, unless anyone's been living under a rock. This has been part of our life for more than a year, actually 15 months now. As of currently, there's over 3.8 million confirmed deaths, despite unprecedented interventions around the world. The estimated total humanitarian and economic cost is extremely high. And there has been significant increases in unemployment and poverty around the world, and also with mental health issues. So really, I want to first premiere by saying that the whole idea of the COVID analytics, the GRAND project, is to utilize analytics and optimization to help mitigate the impact of the COVID-19 pandemic and to help end it sooner. So this is our website, covidanalytics.io. It contains many different fields of application, from collecting meta-analysis on data to prescribing treatments, calculating mortality risk, predicting epidemic cases, evaluating different policies from governments, allocating ventilators around the world to financial relief planning, and various other things on the website. I've been fortunate enough to be sort of working and leading the subgroup focused on the epidemiological models. And we have a very diverse work on this topic with very fortunately with wide-ranging impact. And our model is called the Delphi Policy-Driven Epidemic Model. It's an epidemic model that's been applied to predicting cases and mortalities with the CDC. It's been applied to vaccine development with J&J's single-dose COVID vaccine. We have used it to work with FEMA on how to optimize vaccine allocation. And we're actually now currently working with Swiss Re and Palantir to understand what's the different facets of COVID-19 costs and how the governments could have done better in the setting under COVID-19. Now, obviously today, given the time, I'm not gonna go through everything, and we're gonna focus on the part of the Delphi and the very sort of timely work on the vaccine. I'll be primarily talking about the work with Jensen with the vaccine development. If we have time, I'll also touch a bit on the optimized vaccine allocation that we did with FEMA. So first, we'll introduce our model, Delphi, which is our model for modeling the COVID-19 spread. And the point here is, why is epidemiological models important? And the reason here is that governments and organizations need planning, need stability about a few months out of what's going to happen in the future, to be able to provide support to people, to organizations, to be able to plan resources such as ventilators or such as building out hospitals. And the problem is that the complexity of modeling this epidemic is completely unprecedented, unlike sort of any epidemic before. And this is really complicated by a multitude of factors. There's data scarcity, which is particularly particularly significant at the start of the epidemic. The amount of government interventions around the world has thoroughly impacted how the epidemic has spread, and thus has made the lives of our sort of prediction models much harder, because we need to take into consideration how the government will evolve into the future. And also because treatments are being developed daily, and now with the vaccination efforts, the total landscape is changing on a daily scale. So perhaps it's not surprising when New York Times, this is back in June 2020, reported on 5 different models of the future. It says these 5 models say very different things. And this is because of the different assumptions and the different sort of modeling techniques that we've been using. And today we'll be talking to you about the orange curve here, which is our model on Delphi. And so really Delphi has 3 key characteristics that we're going to talk about. The first of all, foremost, is a compartmental epidemiological model. Second, it uses adaptive optimization with dynamic parameters to capture the fact that the pandemic is changing rapidly throughout. And the model needs to be able to update to the latest information quickly. And third, we're going to talk about how Delphi allows us to do policy-driven scenario analysis so that the organizations and governments can plan against a variety of scenarios of which other governments are sort of working along. So I'm not going to assume that anyone has sort of knowledge about the compartmental model, so I'm going to do a brief introduction, a sort of a 30-second crash course. But I would imagine some of you here might already be very familiar with what this compartmental epidemiological models are. So these models separate people into compartments as is its name, specifically based on how you sort of are responding to the infection. So if you're susceptible, that means you have not been vaccinated, you have not gotten the disease yet, and you're susceptible to getting the disease. Well, if you're exposed, that means that you have already gotten the disease, but you're not infectious yet. And if you're infected, now you're fully infectious. And finally, sorry, finally, you can be recovered, and which you, in this sort of simple model, you assume that we are immune to the virus, and how people transition between these states are governed by differential equations of the form written here. And really, the key equation here, though, out of this simple but very commonly used epidemiological model called STIR, is this first equation connecting how people flow from the susceptible state to the exposed state, which governs how people get infected. So we're gonna dive, just a little bit into that. So if we look at the state of how people get infected from susceptible to exposed, this equation can be really sort of broken down into these parts. So the dsdt is basically the rate of people getting infected, because it's the rate of people leaving the state of susceptible. And that is equal to the number of contacts, this alpha parameter, which is interpreted as the number of contacts by each infected person per day, multiplied by the total amount of infected population. So that gives us the total amount of contacts by the infected population. So how many of these contacts actually, generate new infections? Well, what's the percentage of population that actually could be infected? The percentage is S divided by N, where N is the total population inside your society. So really what this sort of standard epidemiological STIR model is saying is that it assumes a homogeneous population with homogeneous interactions with a parameter alpha that governs how fast do people sort of transmit the virus to each other. And this is really a very simplistic view of model, but it's performed very well in the past in various epidemics. But there's one sort of key assumption here that is very not true in the COVID-19 pandemic. It's that this alpha parameter here, as written, is fixed, which means that the number of contacts by each infected person over the region of epidemic is fixed. And however, in the context of the COVID-19 pandemic, if the government issues a lockdown, then alpha would reasonably go down as people sort of reduce their number of social mobility contacts. So one thing that we did in the Delphi model is that to augment this alpha term with a multiplicative effect that we call the effect of intervention, this gamma of t. And we reinterpret this alpha term as the number of contacts by each infected person per day under no intervention. So gamma of t is interpreted as the percentage, essentially the percentage remaining of the contacts that you have under the intervention. So if gamma of t is 0.2, then that means that under this intervention, you would have 20% of the contacts that you had before. Now, the key question now becomes, how do you sort of estimate this gamma of t? Even if you could fit some kind of non-parametric gamma of t into the historical data, how would you make gamma of t predictive so that you can estimate this into the future? The idea is that we utilize a parametric function. And a parametric function is shown here, which we divide our expected government response, into 4 phases. We note that here that, this was done in March 2020. So this is by far not sort of a historical looking back analysis, but we were estimating and trying to come up with talking to governments of what the government response is gonna look like at the very start of the pandemic. And we thought there's gonna be 4 phases. The first phase in which the government starts to do something during the pandemic by issuing sort of small or sort of lenient restrictions. And in phase 2, the government's going to impose very strong restrictions onto the population, of which achieves the maximum effect in phase 3. And in phase 4, the government could be relaxing these restrictions, and there could be a resurgence in the amount of contacts among the population, which would lead to more transmission. And this is a particular form of the parametric function that we chose with red numbers, red sort of parameters indicating parameters that we fit to the data to sort of govern how long each of the phases are, how strong each of the phases are. For example, if the parameter C here can take 0, which indicates a complete lack of resurgence and things like such. Now, due to the time constraints, I won't be explaining how and why we chose these specific functions. Why is it arctangent? Why is it exponential? but we do have reasons for choosing them based on sort of their long tail behavior of how they model well the sort of the government response behavior. Now, so this is obviously, the government response isn't the only sort of key effect in this pandemic. So there's also a lot of other key effects that we need to model. Number one is the under-detection of cases. So unfortunately, COVID-19 is very similar to other sort of common diseases, such as flu and etc. And so there's a lot of under-detection of cases, specifically in the start of the pandemic, where there weren't even enough testing kits. And so we incorporate detected and undetected states to model missed cases. And another sort of key effect is that the rate of people who are sort of unfortunately dying and recovering are at very different rates. This is something that's not captured under a standard epidemiological model under simplifying assumptions. But in the COVID case, a lot of people recover much more slowly than the people who die. And thus we separate out the modeling of the recovery and death processes. And we also utilize time-varying mortality rates to acknowledge that the treatments have been changing over time, also with the variants, so then the mortality rates could be, broadly changing up or down as time goes along. So, with these sort of modeling efforts, and then the final Delphi model is shown here in this full glory. As you can see, it's very much an SCR-based model, but we separate out the models into various categories based on if they're detected, if they're hospitalized, if they're quarantined. And obviously, we modeled, if people are dying, not, and sort of various dynamics throughout the process. So now, with all of these characteristics, how does Delphi actually perform? So Delphi actually performs quite well, both across regions and across time. First of all, Delphi is one of the only few of the models that predict for all 6 populated continents. So if you go on our website today, you can see that Delphi is predicting for all 6 populated continents around the world. It's consistently the best performing models for deaths in the United States 1 month out, which is really sort of the hardest indicator that the CEC records on a daily basis. As you can see, the blue curve indicates the rank of Delphi, this is among the period from July to September compared to competing models. Here rank being lower is rank being closer to the bottom is better, and sort of really sort of crucially, Delphi predicted the exponential worsening of the pandemic in the United Kingdom, Russia, South Africa, and Brazil more than 14+ days in advance. In fact, that we got some concerning emails from various peoples in those countries saying that our predictions were clearly wrong. There's no way that Russia would have 2 million cases by the end of May, given that they only have 200,000. Unfortunately, we were proven right. And this really shows again sort of the unintuitive nature of the exponential nature of a pandemic. And recently, Delphi correctly estimated both the peak magnitude and the timing of the India's recent second wave weeks before the peak actually arrived. And we're actually working with state governments there on this. So now we have a good sort of epidemiological model. So what are we going to do about it? And the first application that I'm going to illustrate here is that we're going to try to help vaccine development. And before we talk about how we're going to help vaccine development, we're going to first briefly introduce what's the standard vaccine development process. So the standard vaccine development process has sort of 4 phases. First is the preclinical phase, in which the experiments are usually they're done through animal experiments, of which the period could vary greatly between 1 to 5 years, some even taking up to 10 years to go through animal experiments. Then in phase 1 experiments, in which is primarily safety testing, 20 to 100 subjects enrolled into a clinical study of 3 to 12 months to test if the drug is extremely toxic to humans, if it's well tolerated, and things of that sort. And then in phase 2, we start to observe what's the effect of the drug, and does it actually improve the patient in some way. And this will usually carries a subject of 100 to 300 for a time of 1 to 2 years. And finally, in the phase 3 process, the vaccine, goes through a large-scale randomized clinical control trial to test if there's any sort of rare side effects and what's the efficacy in the real population like. And this process often takes 2+ years, and in some sort of rare disease cases, it takes 5+ years. Now, obviously, these timelines here are not acceptable for the COVID vaccine, given the high humanitarian costs and the social costs that we are enduring. So during the COVID race into the pandemic, everything has been squashed to a bare minimum. The preclinical process was done in a lightning phase of up to 2 to 4 weeks. And often among actually most of the vaccines that are currently deployed today, phase 1 and 2 trials were being done together with testing efficacy and safety at the same time, with a larger subject and a much shorter timeline. And the phase 3 trial has been greatly expanded to over 30,000 subjects in hope that the trial will be completed in less than 6 months. However, you can see that in this COVID race to vaccine, what's taking up the most time is still very much the phase 3 trial, and 6+ months is still a very long period of time, especially during the pandemic. So the key question is, can we sort of help accelerate the phase 3 trial of the COVID-19 vaccine? And really, as I said, given the outsized humanitarian and social costs, accelerating phase 3 trials directly saves lives and also help rebuild the economy. The core idea of the phase 3 trials is that you have 2 groups, the vaccinated and placebo group, and you give only the vaccinated group the vaccine, and you give and you wait for the participants to develop infections, and you hope that there's a large differential between the vaccinated group and the placebo group sometime into the future. As indicated in this case, 4 out of 5 people in the placebo group got the virus, where only 1 out of 5, got in the vaccinated group got it. So given a large sample enough size, we can conclude that the vaccine is indeed effective. The problem is that there is this waiting process. And thus, this waiting process highly depends on how fast the infections develop in the placebo group. And therefore, selecting sites with high COVID-19 incidence rates can accelerate the phase 3 trial safely without compromising results, or necessarily sort of resorting to human challenge trials in which we sort of deliberately infect people with COVID-19. And the problem is, though, due to logistic challenges, phase 3 clinical trial sites must be selected almost 3+ months in advance, way beyond the limits of the epidemiological models in the COVID-19 epidemic, even beyond the limit of Delphi, which we have shown roughly it is predictive up to about a 2-month regime. And the reason is because, one of the core reasons is because that the government policies are constantly changing over time. And it's very hard for us to predict how the government response is going to change, 3+ months in advance. So, for example, this is just a graph, of British Columbia, Canada, where it come from, and you can see that there's a lot of changes throughout time of how the government has responded, and this is graphing the reproductive number, of the virus. We have reopenings, then we have indoor dining openings, but we massively then just had restrictions imposed again, then the vaccinations came along, then when there was another circuit breaker, then there was another step on reopening, and I'm sure many of you are perhaps unfortunately too familiar with this process. And thus this brings us sort of, how can we make the predictive model sort of long-term still valid? And one way to do so is that we can consider how the epidemic will evolve under a range of government policies in the idea of using scenario analysis rather than sort of giving one curve, to predict the future. But to do so, we need to understand how the different government interventions actually affect the infection rate of the pandemic, so that we can say, if we're under intervention A, what will happen? Under intervention B, what will happen? Now, thankfully, thanks to our sort of intervention modeling in the Delphi model, we can do this just utilizing the setup in the Delphi model without doing anything sort of beyond that. And the way we're doing it is as follows. Just a refresher here, the Delphi model models the infection rate in the following way, in which gamma of t records the effect of interventions in a parametric model. So say for a particular country, on these dates, we record the gamma of t as fitted by the Delphi model in these regions, and the actual implemented policy in the regions where, say lockdowns, school closings, and mass gathering restrictions. This is here only for illustrations. Obviously, governments might not, change these policies so quickly over time. But using this sort of table, we can actually extract what's the average effect of the intervention under a given policy by just averaging over the gamma of t over the policy of which it was active. And this gives us an understanding of what's the effect of different policies. Obviously, different governments around the world have implemented very different policies, so we've had to categorize the policies in some way or shape or form. And here's how we did it. So we basically categorize the policies, by if you're restricting mass gatherings, if you're restricting businesses, schools, work, and etc., or if the government's implemented a lockdown. As you can see, if under no measure, obviously there's sort of no effect on the natural infection rate. And if as we go down to more restrictive policies, the gamma of t, the average gamma of t that we record around the world, so this is a meta-analysis around the world, is decreasing over time. As you can see, as we move to lockdown, the retained infection rate or the retained contact rate is only 24% of the rate under no measure. And sort of these numbers enable us to do the scenario analysis by basically looking at this point in time, we basically change gamma of t in a smooth manner to the gamma of t indicated by one of those policies, and basically see how the policies would advance into the future in terms of the rates in the epidemic. And so this allows sort of in our case, sort of the vaccination, the pharmaceutical companies to look at this and see, okay, so if the government's implemented different scenarios, what would the infection rate look like? And would our vaccination trials still be okay if the government's implemented sort of different scenarios under these conditions? And so here are results from the actual JNJ phase 3 vaccine trial, which utilized the Delphi-driven scenario analysis to select and to determine their phase 3 clinical trial sites. The predictions were 90% accurate in identifying high incidence regions that would allow the vaccine trial to succeed, and allow also, because we identify the high incidence regions correctly, and high incidence regions are regions that are much more likely to produce variants, and allow the JNJ vaccine to be tested against variants in the trial itself, and thus, and enable the very quick approval process against various organizations. As you can see, most sites that we have chosen exceed the 1.4% analyzed incidence that is required for the vaccination trial to go through. And due to this, the phase 3 trial was accelerated by more than 8 weeks. And while the number of required participants dropped 25% from an initial estimate of 60,000 people to 45,000 people. And there has been currently over 20 million JNJ vaccinations worldwide in South Africa, United States, various European countries. And this trial acceleration process using Delphi has saved up to thousands of people's lives from deaths due to COVID-19. So really here, it's a story about how we can try to end the epidemic sort of sooner. Now, one other thing that I'm only here going to briefly talk about, as I'm aware time is running out, is how we also apply the Delphi model in the context of vaccine allocation. So I'll only briefly talk about what's the context of this. The context is that in January 2021, the new US administration announced the plan to vaccinate 100 million people in 100 days. And as part of the plan, the federal government will open 100 mass vaccination centers around the country to speed up the uptake. And given that the vaccines were sort of very limited in the early stages, and there's also a large variance in epidemic dynamics across the country, it's sort of a key question to where do you allocate the centers so that you can try to end the epidemic the earliest. And how we did so is a multi-stage plan that will only go through the high levels here due to time constraints. And the high-level plan is to do as follows. First, we will try to determine where to locate the vaccination centers by prioritizing national hotspots while ensuring nationwide equity. Then within the vaccination centers, we will have to decide how many vaccines to distribute in each center by prioritizing dynamic hotspots over time, while also ensuring national equity so that no state, has too few vaccines and no state has too many vaccines. And then after we decide which center gets what vaccines, we have to decide who to vaccinate in each center, of which we work with FEMA and CDC to prioritize vulnerable populations, while also ensuring local equity so that no county level is sort of deprioritized and no protected classes disadvantaged. And after we decide all of this, we can then sort of simulate the infection dynamics in each region using the vaccination plan through the Delphi model, which gives us the death toll of the pandemic. And the whole process is repeated throughout so that we can actually optimize over where to choose the vaccination centers and all of the decisions that we need to make as follows. The full optimization formulation is shown here. I'm obviously not going to go through the key here, but we're going to sort of, this is our objective function, is to minimize the cumulative deaths. And there's various constraints that we consider, including budgets, how to distribute vaccine allocations, the interactions between vaccines and epidemiology, how to implement fairness constraints and smoothness constraints so that they can actually be implemented so that, for example, California doesn't get 1 million vaccines today and 202 vaccines tomorrow. And we also included in the optimization formulation the full Delphi model in a discretized way so that it can be included. The final optimization model is actually a nonlinear model due to the fact that that there's an interaction effect between the susceptible population and infected population and the epidemiological model. So to solve this, we actually use two steps, is that we try to optimize and then we simulate. So what that means, so there's an interaction effect that makes it nonlinear, which is that we have this S times I term. So we first fix I, we fix the total number of infections, and we optimize the vaccine's allocations, which gives us a mixed integer linear programming problem that we can solve using standard solvers. Now, after we have the vaccine allocations, we then simulate the pandemic spread using Delphi. And we sort of iterate this through time, through a coordinate descent process. And so this is how we actually solve the model. So what is our actually final solution? So this is how we allocate the centers in the final solution. As you can see, Texas has a lot of centers, California also, and various states like New York and etc. As you can see, some of the fairness constraints are showing here. For example, each state needs to have at least one mass vaccination center for fairness reasons and things of such. So, but what does our sort of result qualitatively say? Our result, sorry, before that, what does our sort of result do? If we compare to some standard baselines that the CDC and the FEMA was considering, which is if we just allocate, for example, baseline one is we just allocate the 100 centers in the 100 most populous cities in the United States. Then the total number of lives saved by the vaccine over a 3-month period that we were considering is 19,000 people. But if we utilize the proposed optimized formulation, then we can save up to 23,000 people, which is a 20% increase. And what that means is that effectively each vaccine, if we utilize the optimized formulation, is worth 1.2 vaccines in life saved. And we could save up to 4,000 extra lives in a 3-month period. So as I said, so what does our solution actually do differently from the baselines? So if you look at the vaccine allocation per capita in state, and so here gray means less than a share of population and blue means more than a share of population. What here we're having is that we're over sort of we're over allocating vaccines into states like Texas, Florida, and New York, and under allocating vaccines into California, the Rust Belt states, and etc. But even under that sort of allocation, the number of deaths in California doesn't actually increase significantly. And this is because at the time that we were considering allocating the vaccination center, the epidemic in California was already in full decline. So thus the incremental benefit of allocating more vaccines to California was much less than allocating more vaccines into states that had hotspots such as Texas and Florida and etc. And so this is really our key result is that the qualitative results is over allocate in these states and under allocate in these others. And so what was the actual implementation? So since our collaboration with FEMA and CDC, the federal
Michael,
government...
I just want to encourage you to wrap up. This is such an important talk that I'm happy to give you a little extra time, but please.
Yeah. So look, this is that slide. This is the last slide. So.
Perfect. Thanks.
So since our collaboration with FEMA and CDC, the federal government has updated its plans so that the states retain control over vaccinations. So unfortunately, we did not build 100 sites. We built 24 sites, but we did incorporate the high-level strategic recommendations to override states, including Florida and Texas. And furthermore, the tactical allocation of vaccines, like how the day-to-day vaccines were allocated, were influenced by the model recommendations. And the modeling showed that the optimization could have a significant impact on the effectiveness of the vaccine. And that's all. Thank you very much.
Wonderful. That was a fascinating talk. Thank you. So even though we're over, we have a gap after the session. So I do want to give people a chance to ask questions if they have them. So please raise your hand or put something in the chat and I will recognize you and unmute you.
Hi, I had a question.
Go for it, Isaac.
Sure. So I was noticing that it seems like in your Delphi model, there wasn't a distinction between if someone is aware of themselves being infected versus if sort of medical actions are being taken on that. Like intuitively, even if a person isn't quarantined, if they feel sick, for instance, they're less likely to spread a disease than even if they don't know it's COVID specifically. So I guess what I'm saying is, like, are tweaks like this easy to incorporate into your model, or do you get into like overfitting or other problems like this?
So I think the key here, is that Delphi at the end of the day, it's a compartmental sort of driven model. And compartment-driven models is aimed to sort of capture sort of large population dynamics. And I think in this case, it will be easy to actually incorporate, what you said into the model is effectively adding another state. But what we did, to sort of incorporate in the state is to basically effectively treat these people as sort of undetected in a way, because they do not know that they're sick. And, if they're the effect of their quarantine is perhaps driven more by the government response, which we've already taken into account in this stage, rather than their actual quarantine reducing their impact on their transmission. So we separate these two impacts, and hopefully that's what we're thinking, is that hopefully this has already contributed or taken care of what you have described. But obviously, yes, you can incorporate more states into Delphi. But as you said, especially at the start of the epidemic, we did not have too much data that enabled us to, do too granular optimization, if that makes sense.
That makes sense. Thank you.
Perfect. Any other questions that you'd like to ask right now? Okay, we're over, so I'll be brief. I won't sit here and wait too long for questions, but that was really fascinating. I love seeing the example of theory meets practice, and this is really great. So thank you again. I didn't give you the applause the first time. I'll give you the applause this time. And now I'll ask Ayush to come onto the stage and share his slides.
Can you hear me?
I can hear you.
Oh, I think the host has to give me permission to start my video now.
Let me try. Does that work? I didn't.
Yeah. It just worked.
Okay,
you can see
perfect.
me now, right?
Great. So our last talk in this session is again from a different area. This is a eclectic session, and this is from an area where in recent years there's been increasing interaction between authors that publish in SIGMETRICS and the machine learning community, but specifically the CULT community, which is a learning theory community, and there's been a lot of back and forth between people in those two areas. And so this is, again, an award-winning talk in that session. I think this was an honorable mention for the best presentation. So that sets a high bar for this presentation, I guess, Ayush. And with that, I guess we see the co-authors on the paper here. And I'll pass the mic to you, Ayush. Thank you.
Thank you, Adam. Cool. So this is joint work with Yossi Arjivani, Yair Karma.
Oh, Ayush, we're seeing your presentation view rather than the slide view, actually. Right
now. I see. Interesting. Let me stop the share. Sorry, give me a second.
No problem. And I should, while you're doing that, I guess I didn't give your affiliation. So Ayush is a PhD student at Cornell, advised by Karthik Sitaran and Bobby Kleinberg. And so he's, that's his background there. Both of those people have, I think, been at least come to SIGMETRICS at least once, but are primarily in the learning theory community.
Wait, do you see the
that looks better? Yes, thank you.
Great, thanks. This is joint work with Yossi, Yair, John, Dylan, and Karthik. So in a typical machine learning setting, we are given a training data. For example, pictures of cats and dogs and their corresponding labels. And we are given a set of models, for example, weights of a neural network. And for every model in this model class and every data point, there is a loss function, f of xz. And what the learner cares about is the test loss, which is the expected loss where the data sample z is drawn independently from some distribution d. And the learner cares about finding a good model for the problem, specifically a point x hat, which is epsilon suboptimal. That is, the test loss at the model x hat is comparable to the best model in this class up to an epsilon additive error. Now, if the learner knew the function f or knew the test loss f, then this is a deterministic optimization problem. However, machine learning setting or stochastic optimization setting, the learner does not know the test loss. Because the learner does not know the distribution D from which the samples are drawn. All the learner has access to is IID samples Z1 to Zn, which is drawn from this distribution D. So the question is, using these stochastic samples, how does learner find a good model, right? Now, if the function f is convex, as is the case in many machine learning problems like support vector machines, boosting, lasso, etc., we know how to solve these problems very well. Our favorite stochastic gradient descent algorithm is the optimal algorithm for learning in this setting. But modern machine learning problems are not convex. If you look at deep neural networks, matrix completion, etc., they have a lot of spurious stationary points, saddle points, local minimas, etc. And in general, when working with such non-convex models, one cannot hope to find approximate global minima. In fact, finding approximate global minima is computationally intractable. Even finding approximate local minima is computationally intractable. However, we train deep neural networks on a daily basis. And these gradient-based optimization methods like SGD, ADAGRAD, etc., they learn very well in practice when optimizing on these non-convex models. Particularly, these gradient-based methods, when working with these non-convex functions, converge to an approximate stationary point of the test loss. And this has been empirically observed. And theoretically, one knows that for many non-convex models, converging to an approximate stationary point suffices to give guarantees on the performance of the model. So this motivates the main question of this talk as to how do we find these approximate stationary points in the stochastic non-convex optimization setting. Specifically, we assume that learner wants to work with a smooth and potentially non-convex test loss f, and wants to find epsilon approximate stationary point for f. That is the point where the norm of the gradient of the test loss is smaller than epsilon. In our model, we assume that the learner can access information about f through stochastic pth order queries. Specifically, whenever queried at a point x, the learner gets to see stochastic unbiased estimates of the derivatives of the test loss up to the pth order. For example, when p equal to 1, the learner gets a stochastic unbiased estimate of the gradient of the test loss. When p is equal to 2, we get a stochastic unbiased estimate of the gradient and the Hessian, and so on. Furthermore, we also assume that besides being unbiased estimates, the returned estimates also have bounded variance under the corresponding operator norm. And we also assume that when we are working in the pth order query model, the test loss is pth order Lipschitz, and that the learner has an initial point x0, which has bounded suboptimality. So all these assumptions are very mild and easy to satisfy for many non-convex problems. And the main question that we're interested in is how many such pth order stochastic queries are required if we want to find an epsilon stationary point for the test loss. All right. Now, let us start by looking at what we know in the deterministic or noiseless case. So here we assume that when we query, instead of getting stochastic estimates, the learner gets to see the exact derivatives of the test loss. What do we know here? What are the rates for different values of p? So here the rates are well understood. Specifically for p equal to 1, it was shown by Nesterov in 2012 that gradient descent achieves the optimal rate of 1 by epsilon square, number of queries to find an epsilon stationary point. And there have been extensions to higher order information where it is shown that in the pth order model, the number of queries for pth order derivatives required is 1 by epsilon to the 1 plus 1 by p. And this is tight due to recent lower bound by Karman et al. So the key idea here is in the deterministic or noiseless setting, rates improve with access to higher order information. And this is expected, right? Like if you get more derivative information, you get more information about the function. So you are expected to be able to find the stationary point faster, right? But is it also the same in stochastic case where there's added noise in the returned estimate? Let's see what we know for p equal to 1 setting. So here on every query, the optimizer observes a stochastic estimate of the gradient. And when the p equal to 1 setting, so it only observes a gradient. So in this case, it was shown by recent work by Gardimi and Lan that we can find an epsilon stationary point in 1 by epsilon to the power of 4 number of iterations. Right, and this was also shown to be tight by Arjivani et al. So specifically in the noisy setting, we have a tight characterization of how many queries we need to find an epsilon stationary point. And it's also not surprising that the rate for the stochastic setting is worse than the rate for the noiseless setting because of the added noise in what we observe. However, one interesting observation is at least for p equal to 1, this exact rate of SGD can be attained if we pick the corresponding deterministic algorithm. And instead of plugging in the deterministic derivatives, we collect sigma square by epsilon square fresh draws per iteration, take an empirical average and plug in the approximate estimated derivative. So all we need to attain this optimal stochastic rate for p equal to 1 is to pick up the corresponding deterministic algorithm, draw sigma square by epsilon square per iteration, and then run it with the empirical average of the derivative at that on those samples. One can repeat the same procedure for higher order information as well, right? For any p, pick up the corresponding algorithm, draw fresh samples, estimate the derivatives, plug in the deterministic algorithm. And this hints at the fact that maybe the stochastic rate is exactly deterministic rate times sigma square by epsilon square. Since 1 by epsilon to the 4 is optimal when p equal to 1, maybe this strategy of picking the deterministic rate and drawing fresh samples per iteration is also optimal for higher order information. Or, sorry. Right. And so is the curve for stochastic case exactly the curve for deterministic case shifted up to compensate for these fresh samples? Or like how much does higher order information help in stochastic non-convex optimization? In our work, we show that this is indeed not true. And in the stochastic setting, having access to second order information or Hessian information improves the rate for finding stationary points. But beyond Hessian, there's no further improvement. This is what we call an elbow phenomena at p equal to 2. Specifically, we show that we can find an epsilon stationary point for the test loss in 1 by epsilon cube stochastic gradient and Hessian vector product queries. We also show that even if we get higher order queries, any stochastic algorithm requires 1 by epsilon cube number of queries. So this shows a stark contrast between the deterministic non-convex optimization and stochastic non-convex optimization. In the deterministic case, access to higher order information strictly improves the rates, but that is not true when we have added noise. In addition to the goal of finding stationary point, we also resolve the complexity of finding epsilon gamma second order stationary points in our paper. Right. Now let us see how we derive this 1 by epsilon cube upper bound for finding stationary points in the second order setting. Here, our algorithm is essentially based on trying to estimate the gradient of the test loss. And the key idea is, suppose we want to estimate the gradient of the test loss at a point xt. And additionally, suppose we have a previous iterate xt minus 1, and we know the gradient of the function test loss at the point xt minus 1. We can simply estimate the gradient at xt by trying to estimate the difference between the gradients at point xt and xt minus 1. And this motivates the direction. Can we estimate this difference using stochastic second order samples? And the key idea is, yes, if you note the difference between the gradient at any 2 points is nothing but a path integral of a Hessian vector product along the line joining the 2 points. This follows from a straightforward application of fundamental theorem of calculus. And what we can do is we can compute this integral by drawing samples. So suppose a grid of k points on the line joining x and y. Just approximate this integral by computing this Hessian vector product on the k points on this grid. We show in this work that if you choose k to scale appropriately, specifically, if you choose k to scale with respect to the distance between the 2 points squared, this ensures that the above numerical estimation does not have too much of an error. And this is the key idea of our gradient estimator. We pick up the gradient at the previous point, estimate the differences, add the difference, compute the gradient, and repeat. This leads to a little bit of extra noise per step. And to compensate for that noise, we need to add a fresh restart after every few steps, which we can do in a randomized fashion. But the gradient estimator is essentially using a Hessian vector product along the on a grid between the sequence of iterates and compute the gradient. We can show that after adding this randomization for restarts, the estimated gradient guarantees that the return point is close to the gradient of the test loss up at the queried point up to an epsilon error. And thus our algorithm is just pick up this gradient estimator and run gradient descent. So for t iterations, start with a dummy gradient estimate, compute the gradient on the sequence, and just run simple gradient descent. And we can show that if you follow this strategy, you can find a epsilon stationary point, specifically the average point computed by this algorithm has epsilon gradient, is epsilon stationary. And the total number of queries needed is 1 by epsilon cube. We can also extend this gradient estimator to use with other algorithms, for example, cubic regularization from Nesterov and Polyak, where it's a fully second order algorithm. So they improve over some dependence on the problem dependent parameters under the order notation. But the key idea is just to use the Hessian vector product based gradient estimator with any other optimization algorithm for the deterministic case. Furthermore, one thing to note is even though our Hessian vector product estimator is using the information about the Hessian, it only uses it through a Hessian vector product. And for many problems, non-convex problems, including deep neural networks, the running time to compute a Hessian vector product is comparable to that of computing a gradient. We can compute Hessian vector products using backpropagation algorithm. So even on the implementation side, using the second order information is not as bad for many problems that we care about. Now, one thing to note is this 1 by epsilon cube rate in non-convex optimization was previously obtained, but under a slightly different query model. In the previous works where this rate was obtained, they assumed that the algorithm can query at 2 points simultaneously and get a stochastic estimate for the derivatives on the 2 points for the same draw of z. So here you can query at 2 points x and y, and you get a gradient at the function for the function at point x, and the gradient for the function at the point y, but for the same value of z. And you can see how this helps, right? Like if you want to estimate the difference between the gradients, you can just simply compute this using an empirical average on the difference between these stochastic estimates, since the z is same for the two parameters. But in addition to this oracle, these works also require additional assumptions on how these stochastic gradients are generated. They assume that the function that generates the stochastic gradients is smooth in expectation. We know that our model is different, very different from this previous 2-point query model. In our case, you can't force z to be same when queried at 2 different points x and y. Furthermore, we can show that the mean square smoothness assumption in the past work and the 2-point query assumption implies our query model, but the reverse is not true. So our version of stochastic tth order query model is strictly more general than what the prior works have considered in similar settings. Right. Now, let us see how our lower bound of 1 by epsilon cube comes up. We show that for any algorithm that uses higher order information for p greater than 2 must query at least 1 by epsilon cube times for some function to find a stationary point. Our lower bound follows by constructing this idea of stochastic zero chains. Stochastic zero chains have been recently used by Karman et al. And Arjivani et al. To give lower bounds in similar settings. But the core idea of a zero chain was introduced by Nesterov in 1998. The idea is, okay, you are given a function where the variable x has p coordinates, and they're linked to each other in a chain-like structure. If you look at the function in the box here, x1 is linked to x2 through the function in the bracket, and x2 is linked to x3, and so on and so forth. The idea is we construct these functions psi and phi as follows. The function phi represents a linear function which is tapered off when x is larger than 1 or minus 1. And the function psi represents a smooth version of an indicator. And the initial point that we considered is x0 is 0. So the key idea is at the initial point, suppose x1 is equal to 0, the first coordinate of the initial point. Here the function phi has a large derivative. The derivative is almost 1. Right. So if you want to make the derivative of this function small, we need to push the first coordinate to be either lesser than -1 or larger than -1 on these flat regions. But as soon as we push the first coordinate to be large, the psi function turns on because this is like a smooth indicator. So it's not active for small values of x1, but as soon as you push x1 to be larger than 1, the psi function turns on. And as soon as the psi function turns on, the phi for the next coordinate appears from the second link in the chain construction. So the idea is you start at all zeros, you have a high gradient because x1 is 0. You need to make the gradient small, so you push x1 outside of the interval -1 to 1. But as soon as you do that, you start the effect of x2, which is 0 because of initialization. Now you need to push x2 outside, and so on and so forth. So if you want to make the gradient to be small for this function, you need to push all the coordinates of the point x to be outside the interval -1 to 1. And in order to push that, you need to take t steps of gradient updates. Now on the stochastic oracle, it's very simple. It's almost a deterministic oracle, except at the leading coordinate, the leading non-zero coordinate. And on the leading non-zero coordinate, we reveal information depending on the outcome of a random variable z, which is drawn from a Bernoulli distribution with bias b. So the idea is if z turns out to be 1, we reveal the information about the gradient to the function. But if z is it turns out to be 0, we do not reveal any information to the oracle. So we can show that with this stochastic model of the oracle, any algorithm needs at least 1 by b samples to even see a single gradient at the leading coordinate. And thus, you need to wait for 1 by b number of queries to make progress by 1 step. And as we showed before, we need to make all the coordinates to be larger than 1 if you want a gradient to be small. So this shows that the number of queries that we need is of the order of t over b, and then properly setting t to be t and b to depend on epsilon, we get the desired lower bound of 1 by epsilon cube. Right. So now I'll quickly give our results on second order stationary points and then conclude, because I think we are close to the time. So in terms of second order stationary points, non-convex functions have a variety of stationary points, right? Like there could be first order stationary point, local maxima, local minima. We define a second order epsilon gamma second order stationary point as a point where the norm of the gradient is small and the minimum eigenvalue of the Hessian of the test loss is large. So this is a function which is a stationary point, and locally it looks almost convex, because the function, the Hessian at the point x hat is almost positive definite. And there are many applications of being able to find these second order stationary points efficiently. Specifically, there are many non-convex models where we know that second order stationary points lead to good performing models, but just finding a stationary point does not. So using our ideas of the gradient estimator that we developed for finding stationary points, we can plug it into a stationary point, second order stationary point finding algorithm. And we show that in the second order information model, where the learner gets to see a gradient and a Hessian, we can find a second order stationary point in number of iterations that scales with 1 by epsilon cube plus 1 by gamma 5 and some lower order terms. On the lower bound side, we know that when p equal to 2, we cannot improve over this 1 by epsilon cube plus 1 by gamma 5 term. So our upper bounds are almost optimal up to the dependence on this lower order term. And we also show that when we are looking at higher order information, there is we cannot hope to find second order stationary points in number of queries less than 1 by epsilon cube plus 1 by gamma cube. Our lower bounds in this case are follow through a similar idea of constructing stochastic zero chains. And the way we construct these lower bounds also give new and tight results in the noiseless case for the problem of second order stationary points. Yeah, please look at more details in the paper. So to summarize, in this work, we give a tight characterization of the complexity of finding stationary points in higher order stochastic non-convex optimization. Specifically, we show that having access to second order information helps, but higher order information does not help any further. And this is in contrast to the deterministic setting where we know that higher order information strictly improves the rates. Furthermore, we also give optimal rates using using Hessian vector product based estimator, which is implementable in a lot of non-convex problem settings. And finally, we also resolve the complexity of finding epsilon gamma second order stationary points up to some lower order terms. Great, thank you.
Perfect, thank you. Okay, so that was a great topic. Also, I really enjoyed this whole session. Questions? Please just raise your hand or put it in the chat and I'll call on you. Yes, Wan Lu.
Hello, can you hear me?
Yeah.
Yes.
I'm new about the gradient, so my problem is what can gradient bonds can do for us? Can help us to find the stationary point or something else?
Right, so the problem that we ask in this question is how do you find an epsilon? Let me go to that slide. How do you find an epsilon stationary point of the test loss? Right, and for motivation, for many problems, including like generalized linear models, robust regression, even in control and tabular RL, we can theoretically show that the points where the gradient is small are points with small test loss. So even though the function is non-convex and so on, finding approximate stationary point suffices to give guarantees on the performance of the model. Was that your question?
Yeah, I think, go ahead, Wana.
Yeah, thank you.
Right.
Thank you.
Yeah, and I think that's been a really powerful idea across a lot of fields with those being some examples.
Right.
Other questions? Okay, so we're a little over anyway, so I think that's a good point to end. So I want to thank all of our three speakers again. I really enjoyed this session in terms of highlighting things that are very, could have easily appeared in SIGMETRICS, but are in other communities, and getting some exposure to those communities as a result. And hopefully, the speakers themselves coming and seeing what's at SIGMETRICS as well. So I hope that everybody enjoyed it. And I guess there's a bit of a break now, given that we're over about 20 minutes before the next sessions. And for the next session, you can find the load balancing act in this room. So Sem Borst is going to be the chair. So if you're a speaker in that section, you can hang out and the volunteers will help you get settled. Or over in the Great Wall room, all systems go, and Chalet Ren is the chair. So you can look for him and head over to that room if you're a speaker in that session as well. So thank you again for the talks, and thanks to everybody for listening. That's it for here.